In this section, you will learn about Rolle's theorem and mean value theorem. First up, we have Rolle's theorem, which you can abbreviate RT. If all three of these conditions are met, first, f is continuous on the closed interval a to b. Second, f is differentiable on the open interval a to b. And third, f of a equals f of b. Then there is at least one number, c, which is contained in the open interval ab, such that f prime of c will equal 0. So before we can make this conclusion, we must first satisfy all three of these conditions. So much like you saw when we wrote our epsilon delta proofs, we can use some shorthand for this last statement and say there exists c, which is an element of the interval from a to b, such that f prime of c equals 0. Next, we'll look at an example to see how this works. Here we have to find the value of c guaranteed by Rolle's theorem on the interval from 1 to 9, or explain why it does not apply. So remember, we have to satisfy the three requirements in the hypothesis of Rolle's theorem. So first, we have to verify that f is continuous on the closed interval that we care about. Now on the interval from 1 to 9, we see that we can draw the entire graph without ever having to pick up our pencils. So by the graph, f is continuous on the interval from 1 to 9. Since we have the graph, we can use it to verify the continuity. So we've satisfied step 1. Step 2 is that f has to be differentiable on the open interval. So once again, we are able to use the graph here, and there are no sharp turns, breaks, jumps, vertical asymptotes, or holes. So therefore, f is differentiable on the open interval from 1 to 9. We have a smooth curve here, is what we call it when there are no sharp turns, breaks, jumps, vertical asymptotes, or holes. Since the graph is a smooth curve, we know that it's differentiable on the entire interval. So now we've satisfied step 2. Now step 3 says we have to look at the y values of the endpoints, and f of a has to equal f of b. So in our case, we would need f of 1 to equal f of 9. And we can use the graph to evaluate f of 1. We see that it equals 10. We can evaluate f of 9 using the graph. We see that it is also 10. So f of 1 is equal to f of 9. And that satisfies step 3. So by 1, 2, and 3, Rolle's theorem applies. And we know there exists c, which is an x value on the open interval from 1 to 9, such that f prime of c would have to equal 0. Now remember, when f prime of c equals 0, that means there has to be a horizontal tangent there. And we can see by the graph that there is a horizontal tangent right here at x equals 4. So using the graph, c is equal to 4. So we were able to find the x value where the derivative was equal to 0. And for Rolle's theorem to apply, you have to have a graph that is continuous and differentiable, and the endpoints have to equal each other. When that happens, it's guaranteed that the only way to get from this y value of 10 back to this y value of 10 at the other endpoint is if somewhere along the way the function had to turn around and go back. And at that place where it turns around and heads back, the derivative is going to be 0 there. In this example, find the value of c guaranteed by Rolle's theorem on the interval from 1 to 7, or explain why it does not apply. Remember, we have to satisfy all three conditions of the hypothesis in order to apply Rolle's theorem. So first up, we need to verify that f is continuous on the interval we care about, which is the closed interval from 1 to 7. Because we have the graph, we can see that we are able to draw the entire graph without ever having to pick up our pencils. So we can say, by the graph, f is continuous on the closed interval 1 to 7. So we've satisfied step 1. Now in step 2, we have to verify that f is differentiable on the open interval from 1 to 7. Now here we notice that the graph has a sharp turn. And anytime there's a sharp turn on the graph, we know that the derivative does not exist there. This is at an x value of 6, so we know that f prime of 6 is undefined. So since f prime of 6 is undefined, we know that f is not differentiable at x equals 6. And 6 is contained in our open interval that we care about from 1 to 7. So therefore, Rolle's theorem does not apply. Remember that to make the conclusion of Rolle's theorem, we have to satisfy all three steps of the hypothesis, and because of the sharp turn in this graph, that violated step 2. F is not differentiable at x equals 6, therefore Rolle's theorem does not apply. Find the value of c guaranteed by Rolle's theorem, or explain why it does not apply. We are given f of x equals x to the 4th minus 12x squared, on the interval from -4 to 4. In order to apply Rolle's theorem, we first have to satisfy all three conditions of the hypothesis. So first we have to know that f is continuous on the closed interval from -4 to 4. Now because f is a polynomial, we know that f is continuous everywhere from -infinity to +infinity. Therefore, it will certainly be continuous on a subset of everywhere, which is the closed interval from -4 to 4. This interval lives entirely inside this interval. So we can't make this claim without first having said where f is continuous. We have to know that f is differentiable on the open interval from -4 to 4. So that means since we don't have the graph, we actually need to take this derivative and find the places where it exists. F prime of x is going to equal 4x cubed minus 24x. Now this exists everywhere. So it exists from -infinity to +infinity. There are no x values for which f prime would not exist. Since it exists everywhere, therefore f is differentiable on a subset of everywhere, which is the open interval from -4 to 4. Third, we have to know that the endpoints have the same y value. So let's evaluate f of -4. Remember, we are plugging into f, not f prime. So that would be -4 to the 4th power minus 12 times -4 squared. If we evaluate that, it works out to be 64. Then we check that against f of 4, which would be 4 to the 4th minus 12 times 4 squared, which is also 64. So we just showed that f of -4 was equal to f of 4. So we've satisfied all three conditions of the hypothesis. So now by 1, 2, and 3, Rolle's theorem applies. And there exists C on the open interval from -4 to 4 such that f prime of C will equal 0. Now remember, in this case, we had to find the value of C. So we have to solve f prime of C is equal to 0. So if we plug x equals C into f prime, then that means we will need to solve 4c cubed minus 24c is equal to 0. We can factor out a 4c, and we would have left c squared minus 6 is equal to 0. And of course, we would apply the zero product property and look at 4c has to equal 0, or c squared minus 6 has to equal 0. From this first equation, we get c equals 0. And from this second, we would have c squared equals 6. And by the square roots property, we know that c would be plus or minus radical 6. Now what we have to do is make sure that all of these values are in the open interval between -4 and 4. Well, certainly c equals 0 is in that interval, and we know that radical 6 is approximately equal to 2.4. So then positive and negative 2.4 would fit in this interval. So then that means that the values of c that we found all work, 0 and plus or minus radical 6. And remember that Rolle's theorem does not tell you how many values of c there will be. In this case, there were 3 different x values where the derivative was going to be 0. All that Rolle's theorem can tell you is there will be at least 1. In this example, find the value of c guaranteed by Rolle's theorem, or explain why it does not apply. We are given f of x equals the square root of the quantity 4 minus x to the 2/3 cubed on the interval from -1 to 1. Now, to apply Rolle's theorem, we have to satisfy all 3 conditions of the hypothesis. First, we have to show that f is continuous on the closed interval, in our case, from -1 to 1. Now, we know that radical functions are continuous on their domains. So to satisfy step 1, let's take a look at the domain of f. We will need the expression under the radical to be greater than or equal to 0, because since square root is an even indexed radical, the domain is that you can only have values that are greater than or equal to 0. And because it's being cubed, whatever the sign of 4 minus x to the 2/3 works out to be, it will keep that sign. So if it's negative, it stays negative. If it's positive, it stays positive. So we are going to need 4 minus x to the 2/3 to be greater than or equal to 0 to satisfy the domain of f. So then that means 4 would have to be greater than or equal to x to the 2/3. Now if we cube both sides, so we would have x to the 2/3 cubed on that right-hand side, we would get 64 is greater than or equal to x squared. Now I like to have the variable come first in any inequality I'm solving. So if 64 is greater than or equal to x squared, that's the same thing as saying x squared is less than or equal to 64. Now to solve this quadratic inequality, we get everything on one side. X squared minus 64 has to be less than or equal to 0. And then we can factor this into x plus 8 times quantity x minus 8. And that has to be less than or equal to 0. Now, to solve this quadratic inequality, let's make a number line. From the first factor, we have -8 on our number line, and from the second factor, +8. And now we will do test points. In this interval, we could use a test point of -9, and we would have a negative times a negative is a positive. In this interval, we could pick a test point of 0, and that would be a positive times a negative is negative. And from here, we could pick a test point of +9, which would be a positive times a positive is positive. Now the domain will be whenever this inequality is true. And this inequality has to be less than or equal to 0. So that's going to be true on this interval. And because this interval is a less than or equals to, it's going to include the endpoints of -8 and 8. So the domain is from -8 to +8. Now remember that radical functions are continuous on their domains. We are concerned with the interval from -1 to 1, which certainly lives within the interval from -8 to 8. So therefore, f is continuous on the interval from -1 to 1. So we have satisfied step 1 of Rolle's theorem. Now that we know f is continuous on the closed interval from -1 to 1, we can move on to step 2, where we have to decide if f is differentiable on the open interval from -1 to 1. Now, f was given to us as the square root of the quantity 4 minus x to the 2/3 raised to the third power. We can rewrite f of x so that it's easier to take the derivative as the quantity 4 minus x to the 2/3 raised up to the 3/2 power. Now, when we find f prime of x, we know that's going to be 3/2 times the quantity 4 minus x to the 2/3. The exponent is going to be 3/2 minus 1, which is 3/2 minus 2/2, which is 1/2. And then the chain rule says that we have to take it times the derivative of what's inside, which would be -2/3 x to the 2/3 minus 1, which is 2/3 minus 3/3, which is -1/3. Now we can write this as a rational expression. Now the 3 in the numerator here will cancel with the 3 here. The 2 cancels with the 2 here, so the coefficients are gone. So in the numerator, we will have this radical. We will also have this negative sign. So we have negative square root of 4 minus x to the 2/3. And then in the denominator, we will have the cube root of x. Now notice that at x equals 0, we would have 0 in the denominator. So f prime of 0 does not exist. It's undefined. So that tells us that f is not differentiable at x equals 0, and 0 is in our interval, the open interval from -1 to 1. So that means this function fails at step 2, so therefore Rolle's theorem does not apply. So because f was not differentiable at every single x value in the interval, we're not allowed to use Rolle's theorem, and it does not apply. Next up, we have the mean value theorem, which we can abbreviate MVT. If both of these conditions are met, first, that f is continuous on the closed interval from a to b, and second, that f is differentiable on the open interval from a to b, then there is at least one number, c, in the interval from a to b, such that f prime of c is going to equal f at b minus f at a over the quantity b minus a. Now, these first two conditions probably feel pretty familiar to you because they're exactly the same as the first two conditions of Rolle's theorem. So what's different is we do not have to have the third condition where the y values of the endpoints are equal to each other. So to use the mean value theorem, it's okay for the y values at the endpoints of the interval to be different. Now remember that f prime of c is just going to be the slope of the tangent line at x equals c. And that tangent line slope is going to be the same as the slope of the line that goes through the points a f of a and b f of b. So because this intersects the curve in two places, this is just a secant line. So one easy way to help yourself remember the mean value theorem is to say that you are setting the slope of the tangent at c equal to the slope of the secant through the endpoints. And then, as we've seen before, we can use symbols to replace all of this with there exists c on the interval from a to b such that, and then I won't rewrite this again. So now let's take a look at an example to see how this works. Here we have to explain why the mean value theorem applies and indicate the value of c on the graph. Before we can apply the mean value theorem, we first have to show that our function satisfies the two conditions of the hypothesis. So first, we will need that f is continuous on our interval. Now, our interval will be from 2 until 14, and because we can draw the graph without picking up our pencil, we know it's continuous. So by the graph, f is continuous on the interval from 2 to 14. Next, we have to show that f is differentiable on the open interval, in this case, 2 to 14. And once again, there's no sharp turns, breaks, jumps. So let's start listing that. No sharp turns, breaks, jumps, vertical asymptotes, or holes. So therefore, f is differentiable on the open interval 2 to 14. Remember, when a graph has no sharp turns, breaks, jumps, vertical asymptotes, or holes, we can say that it's a smooth curve. So by 1 and 2, the mean value theorem applies. And that means there exists C on the open interval from 2 to 14 such that f prime of C has to equal f at the end point, which is 14, minus f at the starting point, which is 2, over 14 minus 2. Well, let's figure out what this is. F of 14 is equal to 6, and we have to subtract f of 2, which is equal to 3, and we put that over 14 minus 2, which is 12. So this simplifies to be 3 over 12, which is 1/4. So somewhere the slope of the tangent at x equals c is going to equal 1/4. Now notice when we do this calculation here, we're doing the y value at 14 minus the y value at 2 over the x value at 14 minus the x value at 2. So what we are doing is finding the slope of the secant line through these 2 points. So the slope of the secant is equal to 1/4. And what we are trying to do is find where the slope of the tangent equals that. So remember that the derivative at C gives us the slope of the tangent line at C, and we are trying to set it equal to the slope of the secant line, which we just found out is 1/4. Now, when 2 lines have the same slope, those lines are parallel. So what we are looking for is when the tangent line is parallel to the secant line. Now, if we put the tangent line on the graph, we can see that right about here, the tangent line is going to be parallel to the secant line. So that means this is our value of C that was guaranteed by the mean value theorem. So what the mean value theorem tells us is if we have a continuous differentiable curve, somewhere the slope of the tangent at C is going to equal the slope of the secant line that goes through the 2 endpoints. Now, what you will find out later in this chapter is that is relating the instantaneous rate of change to the average rate of change of the function. Determine whether mean value theorem applies, and if so, find all values of C, or explain why it does not apply. We are given f of x equals the absolute value of x minus 2 on the closed interval from 0 to 4. Before we can apply the mean value theorem, we first have to show that it satisfies the 2 conditions of the hypothesis. Now first, we need for f to be continuous on the interval from 0 to 4. We know that f of x can be written as a piecewise defined function, negative x minus 2, whenever x minus 2 is negative, which is when x is less than 2, or x minus 2 if x is greater than or equal to 2 because that's what makes this argument greater than or equal to 0. So we can make a line graph for f. The changeover point is at x equals 2, and when we are coming in from the left of 2, we have to use negative of the quantity x minus 2, and when we are coming in from the right of 2, f of x is x minus 2. We can plug in all of the values that are less than 2 into the top definition, and all of the values that are 2 and bigger into the bottom definition, so there are no values of x for which f is undefined, so therefore f is continuous for all x, therefore it's continuous on the interval we care about, which is from 0 to 4. If we know f is continuous everywhere, we know that f is continuous on a subset of everywhere. Step 2 says we have to show that f is differentiable on the open interval from 0 to 4. So now let's look at f prime of x, and let's write that as a piecewise defined function. Now let's make a line graph for f prime. We know that to the left of 2, the derivative would be negative 1. So we can write that in here. If we look at 2 coming in from the right, we know that the derivative would be 1. So that handles all the values that are bigger than 2. But we notice that the derivative coming in from the left of 2 does not equal the derivative coming in from the right at 2. That means f prime of 2 does not exist. It's undefined. So f is not differentiable at x equals 2, which is on the interval that we care about, the open interval from 0 to 4. So therefore, mean value theorem does not apply. So this function fails the hypothesis of the mean value theorem at step 2, because we need f to be differentiable throughout the entire open interval from 0 to 4. Since we know that f is not differentiable at x equals 2, the mean value theorem does not apply. In this example, determine if mean value theorem applies and find all values of c, or explain why it does not apply. F of x is equal to the quantity x plus 1 over x on the interval 1/2 to 2. Before we can apply the mean value theorem, we have to show that it satisfies the two conditions of the hypothesis. First, we have to show that f is continuous on the closed interval from 1/2 to 2. Now we know that rational functions are continuous on their domains. So that means f is continuous from negative infinity to 0 union 0 to infinity. Because the only place that this rational function won't be continuous is at x equals 0. That means it's continuous everywhere else. And if it's continuous on this interval, then it will be continuous on a subset of that interval, which is from 1/2 to 2. This interval lies completely inside this one. So we've satisfied step 1. In step 2, we have to show that f is differentiable on the open interval from 1/2 to 2. That means we need to look at the derivative. F prime of x, we will need to use the quotient rule, which we know is f prime g minus fg prime over g squared. So the derivative of the top would be 1, and we take that times the denominator, which is x, minus the numerator, which is x plus 1, times the derivative of the denominator, which is 1. That goes over the denominator squared, which would be x squared. Now this simplifies to be x minus, we have 1 times this x plus 1, so really all we need to do is to distribute this negative sign to both terms. So we will subtract x and subtract 1. Put that over x squared. So f prime is just going to be negative 1 over x squared. F prime exists negative infinity to 0, union 0 to infinity, because the only place f prime doesn't exist is when the denominator is 0, which is at x equals 0. Therefore, f is differentiable on a subset of this entire interval, which is on the open interval 1/2 to 2. This interval would live completely inside this one. So that satisfied step 2 of the mean value theorem. So now we know the mean value theorem applies. So now that we know the mean value theorem applies, we can make its conclusion. So by 1 and 2, remember 1 was where we showed that f is continuous on the closed interval from 1/2 to 2, and 2 is where we showed that f is differentiable on the open interval from 1/2 to 2. That means we know the mean value theorem applies, and there exists C on the open interval from 1/2 to 2 such that f prime of C is going to have to equal f of 2 minus f of 1/2 over 2 minus 1/2. So let's figure out what this is. F of 2 means we have to plug into the function, which is x plus 1 over x. So that would be 2 plus 1 over 2, which is 3/2. So we can put that here. Minus f of 1/2. So that's going to be 1/2 plus 1 over 1/2. Since this is a complex fraction, let's multiply by 1 in the form of 2 over 2. So we would get 1 plus 2 over 1, which is 3. So we can fill that in here, over 2 minus a half in the denominator is 3 halves. So in the numerator, we have 3 halves minus 6 halves. So that would be negative 3 halves over the denominator, which is 3 halves. So this is going to simplify to be negative 1. Now we need f prime of c to equal negative 1. And remember, f prime of x equals negative 1 over x squared. So f prime of c is negative 1 over c squared. Now we need to solve this for c. And of course, we can multiply both sides by negative 1 to clear out the negative, and then we can cross multiply the c squared, so we would have 1 equals c squared, which is the same thing as saying c squared is equal to 1, which by the square roots property tells us that c is equal to plus and minus 1. Now, remember though, our statement where we said c has to be an element of the interval between 1/2 and 2. But negative 1 is not an element of the interval from 1/2 to 2, so we have to reject it. Therefore, we have only one solution, and that is c is equal to 1. In this example, determine if mean value theorem applies and find all values of c, or explain why it does not apply. F of x is equal to cosine x on the interval 0 to pi over 2 and round to 10,000ths place if needed. Before we can apply the mean value theorem, f must satisfy the two conditions of the hypothesis. So first, f must be continuous on the closed interval from 0 to pi over 2. We know that cosine of x is continuous everywhere. So f is continuous for all x, therefore continuous on a small subset of that, the closed interval from 0 to pi over 2. So we've satisfied step 1. Step 2 says f must be differentiable on the open interval from 0 to pi over 2. Now, f prime of x is just the derivative of cosine of x, which is negative sine x. Now that exists for all x, so therefore f is differentiable on a small subset of everything, which is on the open interval 0 to pi over 2. So by 1 and 2, mean value theorem applies. And there exists a c contained in the open interval from 0 to pi over 2 such that f prime of c will have to equal f of pi over 2 minus f of 0 over pi over 2 minus 0. Now f of pi over 2 means that we are doing cosine of pi over 2, which is 0, so we can fill that in, minus f of 0, which will be the cosine of 0, and that's equal to 1. And we have to put that over pi over 2. So simplifying this, we are going to get negative 2 over pi. And that has to equal f prime of c. Now remember, f prime of x is equal to negative sine x. So then that means that f prime of c is just negative sine of c. And we need to solve this equation. So multiplying both sides by negative 1, we have sine of c is equal to 2 over pi. Then to undo the sine function, we need to take the sine inverse of both sides. So we have the sine inverse of the sine of c will equal the sine inverse of 2 over pi. The left-hand side simplifies to c, and on the right-hand side, this is not one of the special angles, so we have to pick up our calculators, make sure your calculator is in radian mode. You would do the sine inverse of 2 over pi, and in this problem, we were told to round to the 10,000ths place, so that would be 0.6901. Now remember, we have to make sure that that value fits in to our interval, which is the open interval from 0 to pi over 2, and 0 to pi over 2, if we did approximate values, is 0 to 1.57. So certainly a radian measure of 0.6901 is inside that interval, so this value of c will work.